Right now, out in the Australian desert, an absolute behemoth of a machine is rising straight out of the red dirt. We are talking about a $6.4 billion megabuild aimed at stopping a national food crisis dead in its tracks. In this explainer, we're digging into the Perdaman Urea Project, better known as Project Ceres. It is literally the largest project of its kind in the nation's history, being built from the ground up on the Burrup Peninsula. Let's dive in and see exactly what it takes to pull off a world-class industrial marvel of this scale. But right out of the gate, this project presents a massive, unavoidable tension. The central question is this: can a $6.4 billion engineering puzzle be solved without permanently damaging 40,000 years of ancient history? You see, we've got an incredibly complex industrial solution on one side, and the preservation of sacred ancient Aboriginal rock art on the other. It's a really delicate balance between progress and heritage. And to fully grasp how we got to this point, we first have to understand the massive problem this factory is trying to solve. Part 1. A national food crisis. Let's take a look at the underlying vulnerability that made this mega build necessary. 2.4 million tons. That is the staggering amount of urea fertilizer that Australia currently has to ship in from other nations every single year. Because they just don't produce enough of it at home, the cost of farming is pushed sky high. But even worse than the cost is the risk. Think about it. If global shipping lanes get disrupted for any reason and those fertilizer ships can't dock, the entire national food supply is instantly on the line. So to plug this massive vulnerability, Perdaman Industries stepped up with Project Ceres. The goal is to completely flip the script, shift away from relying on those vulnerable ocean imports, and start locally producing 2.3 million tons of urea every year. Now, to pull that off, this plant is going to be hungry. It will consume 130 terajoules of natural gas every single day. That gas is coming directly from the Scarborough project, traveling through a brand new $550 million pipeline straight to the plant site near the town of Karratha. Let's quickly trace the timeline here, because it's been a long road. It all kicked off back in November 2018 with a 20-year gas deal signed with Woodside. Fast forward to April 2023, and construction officially began. By mid-2025, the project was already hitting the 66% completion mark, all sprinting toward a finish line in mid-2027. And getting to that starting line was no joke. Contractors CYPM and CL had to put in a Herculean effort. The desert ground out there is so incredibly hard that workers actually had to crush 2.2 million tons of solid rock just to lay down a flat 73-hectare foundation. Part 2. Chemistry of the mega plant. So how do engineers actually take invisible natural gas and turn it into solid fertilizer? Well, the first big piece of this puzzle is the ammonia plant, which is built to churn out 3,500 tons of ammonia daily. To do this efficiently, they're using this cutting-edge technology from Haldor Topsoe called SynCOR. Normally, an ammonia plant means a massive amount of steam to break natural gas down. We're talking a steam-to-carbon ratio of around 2.5 to 3.0. But the SynCOR tech drops that ratio all the way down to 0.6. That is 80% less steam. It's brilliant engineering because it means they can use smaller pipes and smaller machinery but still produce way more ammonia. The whole thing is essentially a 4-step chemical dance. Step 1 is desulfurization. The gas flows through zinc oxide, which acts kind of like a magnet, pulling out the sulfur so it doesn't wreck the super expensive catalysts down the line. Step 2 is the autothermal reformer. This is where natural gas, steam, and oxygen get mixed under extreme heat to literally rip methane molecules apart. Then, in step 3, the gas moves into high-temperature shift reactors, converting carbon monoxide into carbon dioxide and hydrogen. Finally, step 4 squeezes that hydrogen and nitrogen together in an inert-free ammonia synthesis loop. Because there's no waste gas trapped in this loop, it can run at a much lower pressure, which saves a massive amount of electricity. Okay, so you've made all this liquid ammonia. Where do you put it? Well, they built a massive refrigerated storage tank that holds 10,000 tons of the stuff. And the way they built it perfectly captures the crazy engineering happening on this site. The roof of this tank alone weighed 120 tons. But instead of using giant, heavy-duty cranes to lift it, the engineers used something called an air raise. They essentially turn the inside of the tank into a giant balloon, using high-volume fans to create enough internal air pressure to slowly push that 120-ton solid steel roof 38 meters straight up into the sky. Unbelievable, right? Now we move to the second phase, the urea plant. This is where they use stamicarbon technology to mix the ammonia with carbon dioxide. Inside the main reactor, these chemicals are squeezed together under 160 bars of pressure. To put that in perspective, that is 160 times higher than the air pressure we're breathing right now. This chemical mix is incredibly corrosive, so the whole thing is lined with Saphirex, a super duplex stainless steel built to resist rust for 40 straight years. But here is the cleverest part. The plant is located right near an airport, meaning they had very strict height limits. To get around this, engineers used a horizontal pool condenser. They essentially laid the massive tank on its side, saving 10 meters of vertical height and shaving down the foundation costs in the process. So, we have liquid carbonate. How do we get to the solid fertilizer granules that farmers actually put on their fields? It happens through a process called fluid bed granulation. Picture this. Inside a massive chamber, tiny little seeds of urea are kept floating mid-air in a constant stream of wind. While they float, liquid urea is sprayed onto them. As that liquid hits the seeds, it freezes onto the surface, building up perfectly round, solid layers. To make absolutely sure these granules don't break apart into useless dust during shipping, Perdaman actually signed a $90 million deal to coat them with 16,000 tons of a special chemical called UF80 every single year. Part 3. The giant logistics puzzle. Because, as you can imagine, building a sprawling facility of this magnitude out in a remote desert is a logistical nightmare. The Burrup Peninsula is incredibly isolated, so standard stick-build construction just wasn't going to cut it. Instead, engineers opted for a modular build. They're literally fabricating over 100 massive pieces of this plant at a giant yard over in Chennai, India. We're talking 62,000 tons of steel in total. Once built, these giant modules are loaded onto ships and hauled all the way across the ocean to the port of Dampier in Australia. Just to wrap your head around the scale we're dealing with here, the physically largest single module is 42 meters long, 14.7 meters wide, and weighs 985 tons. But the heaviest module? That one clocks in at a mind-bending 2,700 tons. And here's the kicker. Once these monolithic chunks of steel arrive at the port, they still have to be moved the final 2.6 kilometers to the actual construction site. So how exactly do you move a 2,700-ton block of steel across the desert? You bring in self-propelled modular transporters, or SPMTs. These are basically massive flatbed trailers loaded with hundreds of independent wheels that can turn in literally any direction. They crawl along at a painfully slow speed of less than 1.6 kilometers per hour. And they have to go that slow because the road from the port features steep 8% inclines. Moving that much weight up a hill like that requires absolutely flawless timing and coordination, or else the modules could tip over or completely crush the road underneath them. And look, once this whole thing is fully assembled, just keeping it running is a beast of a job. It needs its own dedicated power station generating 101 megawatts from gas turbines, plus another 5 megawatts of solar. It gulps down 25.2 million gallons of seawater every year just for cooling and desalination. And once that solid urea is finally ready, it travels to a massive 75,000-ton storage shed at the port on a 3.5-kilometer conveyor belt. But importantly, this entire belt is completely enclosed in a steel tube. Why? To guarantee that not a single speck of urea dust escapes into the air. Which brings us to the most complicated and controversial part of this entire endeavor. Part 4. Progress versus ancient history. Because the physical location chosen for this plant brings some intensely heavy complications. First, let's talk about the money, because the national government is heavily invested in securing this agricultural win. They've poured massive loans into Project Ceres. We're looking at $220 million from the Northern Australia Infrastructure Facility just for the plant, another $160 million for the port, and $95 million for water pipes. On top of that, Export Finance Australia threw in a $269 million loan. The sheer economic drive to get this finished is immense. But here is the massive catch. The Burrup Peninsula isn't just an empty patch of industrial dirt. An estimated 1 million ancient Aboriginal rock carvings exist in this exact area. We are talking about a continuous cultural landscape that dates back 40,000 years. It is literally one of the most historically significant sites anywhere on the planet. And this is where we hit a profound clash. On one side, you have the economic victory, a facility engineered to produce 6,200 tons of essential urea every single day, effectively disaster-proofing a nation's food supply. But on the other side, there is a severe environmental threat. Many researchers are raising serious alarm bells that the nitrogen emissions from this plant will mix with the atmosphere and create acid rain. The argument is that industrial pollution is already making some of these irreplaceable ancient rocks porous, slowly eating away at a 40,000-year-old legacy.
And this isn't just theoretical, it's already having a physical impact. Just to lay the foundation for this sprawling factory, 3 sacred rock art panels actually had to be removed from their original locations. According to the source material, this specific, irreversible action caused immense pain for the local Aboriginal people. Some elders have explicitly stated they felt they were given no real choice to stop the development from moving forward.
Which leaves us with the ultimate question. You've seen the $6.4 billion engineering marvel, the mind-blowing desert logistics, and the incredibly vital agricultural problem it solves. But you've also seen the permanent alteration of a 40,000-year-old cultural landscape. Is securing a nation's agricultural future really worth the cost of its ancient history? It's a hugely complex puzzle with no easy answers. Thanks for joining me for this explainer, and I encourage you to keep questioning exactly how we balance our future needs with the preservation of our past.